My chairman, ladies and gentlemen, I'm Wang from Huazhong University of Science and Technology of China. This work is co-authored with Yong Xiao, Huixiang, Zijian, Yingyu, and Xiaohu from Huazhong University of Science and Technology. And I'm honored and proud to have the opportunity to share our recent work with all of you. Today, I would like to present my paper toward energy-efficient federated edge intelligence for IoT networks. My presentation will cover the following four aspects. First, I will introduce the background and motivation of my research. Second is the system model and problem formulations. Then I will describe problem optimization analysis in my research. And last is the simulation results and conclusion about my whole work. As the figure shows that with the development of mobile communication technology, the next generation communication technology is expected to support a plethora of new services and applications. Large amounts of unprocessed data generated at the edge of the network an issue. Traditional centralized cloud computing processing architecture is too expensive to process massive data and is no longer suitable for various emerging application scenarios. In this case, we hope to find a solution at the edge of the network close to the user end. Edge computing is one of the key components in the 5th generation mobile communication technology. Users are eager for high quality of service experience. However, data centers are usually located in remote areas. So we introduce edge computing architecture. Edge computing architecture consists of a large number of small computing servers, and the deployment of edge server is closer to users, which can reduce the huge data transmission energy consumption and decrease the burden of computationally intensive tasks on cloud data center. Federated learning is an emerging machine learning framework that enables collaboratively model training, and it has been considered as one of key technology for data processing and model construction based on decentralized data sets distributed across a large networking system. It can protect data privacy and reduce communication overhead. Combining these two key technologies, we propose a new architecture. Our federated edge intelligence system consists of three main components. The coordinator coordinates the model training process among all edge servers. It can be deployed at the cloud data center or one of the edge servers. Those edge servers correspond to mini computational servers deployed close to the IoT devices to provide data storage and model training service. The IoT network consists of a large number of IoT devices deployed across a wide geographic area. Each IoT device collects local data samples to upload to its designated edge server. The main steps of each round are shown in the figure. First is data collection, then is local model training, next is model uploading, and finally is model aggregation. Learning models has increased 300,000 times in 6 years. Correspondingly, the energy consumption used in model training tasks will also increase sharply. This is a problem that cannot be ignored and needs to be solved urgently. In this case, we analyze the problem we should solve and put forward the final research goal. Our research goal is very clear. It's just optimizing the energy consumption of the system and ensuring the accuracy of the training model. This is a very difficult problem. We have the following challenges. First, heterogeneity of energy consumption characteristic of edge computing nodes. Second, the impact of different model training parameters on model accuracy and energy consumption is unknown. And in the end, there are still lack of extensive data measurement research on prototype system. Above all, we modeled the energy consumption during the model training process of FEI system. It consists of three parts. First is energy consumption of data collection, which is dominated by IoT devices in transmitting the required number of data samples. As we can see in the table, row K is the normalized energy consumption for IoT devices to upload each data sample. Then is energy consumption of local model training, which is mainly affected by the energy consumption of local computation and data processing performed by each edge server. Finally is energy consumption of model uploading, which can be modeled as a constant. After this, we could formulate our objective energy consumption optimization problem, where E is local training epoch, K is the number of edge servers that participating in FL training process, T is global aggregation times, and epsilon is target model accuracy. This formulation could represent our research goal very well. And the first constraint represents the convergence accuracy we should ensure, while the second is the basic constraint of those key parameters. It is quite difficult to solve the problem directly. We should seek for other solutions. According to the proposition 1 and proposition 2 in this paper, we complete the parameter substitute. After we complete the parameter replacement, we can rewrite our objective optimization function as below. We analyze the target optimization problem and find that the target problem is only related to K and E. This means that the objective function is a biconvex function. In this way, we also get the closed form solution of the function to K and E. Then our task is to find the optimal solutions of this new optimization problem. For the biconvex problem, we used the ACS algorithm to find the optimal solution. The basic idea of the ACS algorithm is to fix one parameter at one time and analyze another parameters and alternately optimize the target problem for all these parameters to obtain the optimal solution. In this way, we could find the optimal combination of K and E for our problem. Here we present prototype of Federated Edge Intelligence System. We can see that the laptop is used as the coordinator and the Raspberry Pi is used as the edge server. We complete the networking between those devices through the wireless router. FEI systems are deployed on those devices. The power measurement device monitors the power changes on the edge servers during the model training. It can be found that the power change shows regular characteristics, and each round of global training process also shows obverse phase characteristics. Next, we will show the simulation results. we can see that when the number of edge servers k increases, the number of aggregation runs required for the model to reach the target accuracy will decrease. And in this picture, we can see that when the local training effort increases, the aggregation runs required for the model to reach the target accuracy will decrease. Finally, the performance evaluation shows that the theoretical optimized value is close to the real measured value. The model has practical guiding significance, and there is an optimal combination of parameters which can significantly reduce the system energy consumption. Finally is the conclusion. In this paper, we investigated the energy consumption in each step of model training process and proved that the energy consumption minimization problem was biconvex. Then a hardware prototype has been developed to verify the performance of our proposed solution. Finally, experimental results show that our theoretical results are consistent with real energy measurement results, and our architecture could reduce energy consumption by nearly 50%. That's all. If you have any questions, please contact us. Thank you.